Okay, welcome to Learning Module 3C. We're going to talk about line balancing. And the objective here is that you'll understand how to balance a line, group tasks into a logical sequence of workstations at the minimum amount of idle time and the highest efficiency. So let's take a look at how to do that. So what is line balancing? It's a technique used in developing product-based layouts, so sequential production, product-based layouts, that works by assigning tasks to a series of linked workstations in a manner that minimizes the number of workstations and minimizes the total amount of idle time at all stations for a given output level. So at a high level, to understand this concept, what we're basically saying is, and you'll see it in the example, if we have 10 different tasks and they take dramatically different amounts of times, we can combine them into groups that have at least similar amount of times and improve the efficiency of the line from not grouping it at all. It's better balanced than it would have been without grouping these tasks together. Okay, the 6 steps of line balancing. Number 1, we have to identify all the process steps required, their times, their immediate predecessors, and the total time for all the tasks. And we're going to do that in an example. We need to create a precedence diagram. We're not going to draw one here, but I'm going to show you one from the text. We need to determine the takt time, which we did in the last video, but we're also going to do one more time today because we need that takt time. We will then compute the theoretical minimum number of workstations needed that we can group these tasks into. How many workstations do we need? And we'll use a decision rule to assign the tasks to those workstations and then evaluate the performance of the proposed line by calculating some performance measures. These are a couple of things the concepts we need to remember. So cycle time, you remember, is the maximum amount of time spent in any one workstation. So the line's cycle time is dependent on the slowest workstation. We'll see how that plays out here. The idle time is the actual time consumed by these workstations versus the amount of task work that actually had to be performed. So we're trying to, of course, reduce and minimize idle time. The percentage idle time is just a percentage of those same figures, right? So if we take the amount of time idle and the amount of time we had, we'll get a fractional figure that we can use a percentage for. And our efficiency delay is the inverse of that figure. So it's 100% minus our percent idle equals our efficiency delay. So we want a high number for efficiency delay and a low number for percent idle time. That is the goal of our exercise, to have an efficient line with low idle time. So here's the example. Blackhurst Engineering, a small contract manufacturer, they just signed a contract to assemble, test, and package products for another company. So they're an outsourced firm. They do services for other firms. They've quoted a contract and they signed it, and now they're obligated, right? So they must produce 500 units per 8-hour day. And you will recall from our last session that we can find the takt time if we know how many units we must produce in a given period of time. And we will need to do that for this exercise. These are the tasks. So when Blackhurst quoted this work, they had to understand what they were quoting and how much time it would take and what their costs would be, etc. So they broke the work into these 10 tasks. A through J is 10 different tasks that have to be completed to do the work. They also assigned so many seconds to each task, right? And as listed here. And they've said which tasks needed to be done before another could be started, predecessors. Okay, so A has no predecessors because it is the first task. B is dependent on A. We cannot start B until A is complete. We cannot start C until A is complete. we cannot start D until both B and C are complete. We cannot start, these are linear then, and then F, G, and H are all dependent on E, right? Oh, no, excuse me. Yeah, F, E, G, F, G, F, G, and H. And then I is dependent on that cluster of F, G, and H. And J is dependent on I. So let's take a look at what that would look like in a precedence diagram. So make sure you can understand this, because we need to use this to use a decision rule to build up our number, assign these to our workstations. So we put the times in next to each task, and you'll see that the diagram reflects what we saw up here. It's not A to B to C to D, it's A to B and A to C, because these are both dependent on A, and then D was dependent on B and C, and you see that it flows exactly as it's listed here by engineering. So that's the flow in our plant. That's the process. The other important number on this sheet is the real working time, or the total task time, which is 202 seconds. This is the real work, right? This is the real work. Now, if we had just lined all these tasks up into an assembly line, linear, right, which we could do, we would have a lot of idle time. We would have the slowest task be this 32 seconds, and we'd have other tasks as fast as H here, 10 seconds. So H would be bored, right? They're waiting. They're only working a third of the time. They're idle 2/3 of the time, right? Even a little more than 2/3 of the time. So you get the idea why we didn't just say, let's do a 10-step linear process here. If we cluster these into groups, we can reduce the idle time we would have incurred had we done this as a linear process. Let's take a look now. How do we do it? Number one, we got to come up with the takt time. You remember it from the last session. So we needed available production time and a required output rate to find our takt time. Well, we know we have an 8-hour day, and 8 times 60 minutes times 60 seconds is going to give us 28,800 seconds of available time, and we need 500 units in a day. That's the contract. So our takt time is 57.6 seconds, and you'll recall what that means is the tempo that we must produce a unit in order to meet demand. This is the minimum specification of production that allows us to meet demand. It doesn't consider a lot of real-world stuff like taking breaks, going to lunch, downtime for equipment and so forth. So this is a very simple and optimistic takt time. In reality, if we built our business around that, we'd be asking for trouble, wouldn't we? Because things do happen, and lines don't run 100% efficient. You'd probably take that figure and multiply it times or divide it by 0.85 or some factor to say, no, we can't assume 100% efficiency at our takt time. But for this simple model, there is our takt time. Okay, so how do we find the number of workstations? We take the total time we need to work, the 202 seconds, which was the total of all the items, all the tasks that we totaled up was 202 seconds of real work we need to perform, and we divide it by the takt time. It comes up that we need 3.51 workstations. We have to round up to 4. If we need 3.5, we can't do with 3. We need 3.5 or more, so we're going to need 4 workstations. We would round that up to the next highest number. Let's see what we got next here then is, boom. This is basically the result of following a decision rule and allocating each of the 10 tasks to one of those 4 workstations. We start at the beginning with task 1 and workstation 1, task A and workstation 1, and the decision rule is that we add the tasks, depend on the precedence diagram, we add them in order until we're as high as we can go without exceeding the takt time. If we were to exceed the takt time, our plan is not viable. We will not hit 500 per day. So we add 15 plus plus B, 26, plus C, 15. We're at 56 seconds, and without even adding D, we know that we cannot add D. That 32 is going to put us over 57 point, whatever that was, whatever our takt time was. Okay, so then we go to workstation 2. We had 32 and 25. We're at 57, almost to the takt time. We go to workstation 3, 18 plus 15. Got room for another. Add in the 10. 43. Did not have room for the next one, for I. So we stop at 43, and the last two get added into workstation 4 to be 46. Notice that every workstation must have a total time less than the takt time. That's the decision rule. Okay, leveling involves assigning tasks to workstations while following the rules of precedence and without exceeding the takt time. This is what it would look like then in a if we take our precedence diagram now and consider it as workstations. We can see workstation 1, 2, 3, and 4. We know that none of those exceed. There is a very important item here, though, that you need to remember because it matters a lot, and that is that the longest cycle time of any of these clusters, these workstations, was 57 seconds. That 57 seconds is a bottleneck. It is the bottleneck for this line. This line cannot run faster than its slowest workstation. Its slowest workstation is the longest amount of seconds, 57, almost to the takt time, right? So the rest of these lines will have some idle time, and we'll look at how that works. So station 1, 3, and 4 will also run at 57 seconds, even though they're capable of going faster, because the line is going to run at 57 seconds, the speed of its slowest workstation. Okay, so to calculate idle time, percent idle time, efficiency delay, basically idle time is the actual work minus the time that's available. So it's the time we consume minus the time we needed. So if we take the 4 workstations and the 57 seconds of the slowest workstation, workstation 2, and we know that all 4 workstations are going to run at 57 seconds because they can't go faster than the slowest one, it means that we've got 228 seconds, 4 times 57. So we're going to consume 228 seconds, but we only needed 202 to complete all the tasks. So we have 26 seconds of idle time. Okay, simply put, the total time consumed minus the total time required for the tasks gives us our idle time. The percentage idle time is basically just taking the numerator and denominator view of that and saying that our 26 seconds of idle time over the 228 seconds that was consumed by the line is 11.4%. Okay, so we have an 11.4% idle time. A mistake a lot of people make is not dropping this 228 in here, but only looking at the total task time required. Remember, we required this much, but we burned this much because our design basically forced us to have some idle time. We've minimized it, but there's still idle time in there of 26 seconds. So we've got to use the 228 here as the denominator to get to our 11.4. Remember that. A lot of people make that mistake. Our efficiency delay, which is a number that we want to be high, it's a positive. We want a very low efficiency delay, or a very high, efficiency delay, is 100% minus our percent idle. So 11.4, the inverse of that, 88.6, is our efficiency delay. You could say 100% minus your percent idle time equals your efficiency delay. 100% minus percent idle. So let's do a quick recap to make sure we understood. We built these 4 workstations using the takt time and the total seconds that we needed to work, to allocate those as efficiently as possible using the precedence diagram, we had some idle time at all but one of the workstations, the bottleneck, the slowest workstation. Workstation 1 had 1 second, Workstation 3 had 14 seconds, Workstation 4 had 11, for a total of 26 seconds of idle time. The resulting line is not perfectly balanced, which is normally the case. To have it be perfectly balanced would be a miracle. I don't know if it's ever happened in the history of the world. But it is more balanced and more efficient than this string of 10 tasks all tied into a line would have been. It's an improvement in a reduction in idle time, which we could calculate, and you're free to do. The manufacturing engineers would likely go to work on this line, though, right? So anytime that we build a line, continuous improvement is part of operations. So we quote something, we quote some work, and the first thing that happened is we say, how can we do this more efficiently? We had to quote that lower than we wanted to win the work. How can we go and make money now? So any operation you go into in a competitive industry will say, well, we developed a quote based on what we knew and trying to be competitive, and then we went to work on it and try to become more efficient. So the manufacturing engineers are going to go and reduce this idle time. How will they do it? By looking at the tasks themselves, by looking for any form of efficiency that they can improve and rebalance this and eliminate work, maybe completely eliminate a task, combine tasks, and shift it around to get that 20 seconds of idle time as low as they think they can possibly get it. So here's a question for you to look at it one more time in a different form of analysis. This table depicts a production line that's been already balanced, with 6 workstations, resulting in a cycle time of 2 minutes. What is the efficiency of this balanced line? Well, how do we know that it has 2 minutes? If they hadn't told us that the cycle time is 2 minutes, we'd look down here. If these are the 6 workstations, and we saw that task A and B are in workstation 1, and C, and then D, E, F in 3, G, H in 4, etc. And down here, we see that we've got 1 minute for task A and 1 minute for task B. If we do that across all these cells, we'll see that this is our bottleneck, and this is taking 2 minutes. This is 1.8, so it has a 0.2 minute idle time. This is 1 plus 0.5 plus 0.4. This is 1.9 for workstation 3. Here's 1.7 for workstation 4, 1.8 for 5, and then 5, 5, and 6, 1.6 for workstation 6. So we could take the total of any of these workstations times and subtract it from our bottleneck, and we would know the idle time. And we can add those across and build the answer to this question. So let's do that. So if we add all the idle times for each workstation based on the cycle time driven by workstation 1 of 2 minutes, we would have 0.2, 0.2 here, sorry, it'd be 0 here, and then 0.2, 0.1, 0.98, that should be 0.3, yes, and 0.2, and 0.4. We can add those up to a 1.2 minute idle time by adding up those idle times. The total task time is the cycle time of 2, right? The line cycle time being driven by this 2 minute process times all 6 cells, or 12 seconds. Okay, I'm mixing my minutes and my seconds. Sorry, I got to redo this slide. This is seconds. All this stuff is seconds. Sorry I threw that minutes up there. Okay, the percent idle time would be the 1.2 seconds divided by the 12 seconds, or 10% idle time. 100% minus the 10% is a 90% efficiency delay. So again, 6 times 2, if this is 2 seconds as our longest workstation, we multiply all 6 times that for 12 seconds of total time required and consumed in the line. We have 1.2 seconds idle time by adding up the difference between 2 and the total time worked in each of these, the total task time in each of these cells. That 1.2 divided by the 12 seconds gives us a 10% idle time, and 10% idle is 90% efficiency delay. The lower the idle time and the higher the efficiency, the better. So in summary, line balancing minimizes the number of workstations and the idle time, and it increases the efficiency. It's combining tasks to reduce idle time and improve efficiency. Takt time provides us a baseline to determine the minimum number of workstations and allocate our tasks across those workstations. The slowest workstation will determine the cycle time of the line. The slowest workstation cycle time is the cycle time of the line. It is the bottleneck of the line. Idle time is the time at the workstations with lower time than the cycle time. So we will have idle time in every workstation except our bottleneck. 100% minus the idle time percent is our efficiency delay. I hope you enjoyed and learned something about line balancing today, and that concludes our discussion on that topic.